Welcome to Orbital Dynamics, Part 61. In the last section, we talked about the precession of the argument of perigee due to the Earth's oblateness. It's a bulge around the equator. The Sun also has a bulge, too, that affects the orbits of the planets. The planet Mercury, however, has a bit more perturbation than this predicted. This is recognized by Urbain Le Verrier in 1859. Le Verrier is famous for predicting the existence and position of Neptune. He saw discrepancies in Uranus's orbit and suggested that there was another massive planet. He sent the letter to a colleague, Johann Gottfried Galle, in Berlin. The night after he received it, Galle found Neptune to within 1 degree of the predicted position. This was a dramatic validation of celestial mechanics and one of the most remarkable moments in 19th century science. While he was able to resolve discrepancies in Uranus's orbit, he wasn't able to resolve discrepancies in Mercury's orbit. That wouldn't get resolved until Einstein's theory of special relativity. In 1638, Galileo proposed an experiment to measure the speed of light by observing the delay between uncovering a lantern and its perception some distance away. He was unable to distinguish whether light travel was instantaneous or not, but concluded that if it weren't, it must nevertheless be very fast. The first quantitative estimate of the speed of light was made in 1676 by Ole Romer. He observed that the periods of Jupiter's innermost moon, Io, appeared to be shorter when the Earth was approaching Jupiter than when receding from it. Here's what happens if Earth approaches Jupiter. The green arrow is a beam of light. Because Earth travels towards Jupiter, the time it takes for light to reach Earth is shorter. Here's what happens when Earth recedes. The time it takes for light from Jupiter to reach Earth is longer. These dynamics explain the discrepancies Ole Romer was trying to resolve. He thus concluded that light travels at a finite speed and was able to estimate that light reflected on Io would take 22 minutes to reach Earth. Christian Huygens combined this estimate with an estimate for the diameter of the Earth's orbit and estimated the speed was 22,000 kilometers per second, only 26% lower than the actual value. In his 1704 book Optics, Isaac Newton reported Romer's calculations of the finite speed of light and gave a value of 7 or 8 minutes for the time taken for light to travel from the Sun to the Earth. The modern value is 8 minutes 19 seconds. Newton looked into whether Romer's eclipse shadows were colored. Hearing that they weren't, he concluded the different colors traveled at the same speed. If different colors traveled at different speeds, Romer would have noticed different colors. Instead, he saw white light. The speed of light was the first piece of data Einstein needed to develop his theory of special relativity. Over a century after Le Verrier found the discrepancy in Mercury's orbit, James Clerk Maxwell compiled 4 equations into a coherent theory of electromagnetism. 2 of these equations, when considered together, led to his assertion of the possibility of electromagnetic radiation. Faraday's law states that a changing magnetic field creates a current. Maxwell added that a changing magnetic field could also create a changing electric field. Ampere's law states that a current creates a magnetic field. Maxwell added that a changing electric field could create a magnetic field as well. Maxwell saw that a changing magnetic field would create a changing electric field, and a changing electric field would create a changing magnetic field. Once set up, the 2 fields would self-propagate. They go orthogonal to each other, as you can see from the graphic. This was the advent of radio communications. Maxwell was able to determine the velocity of an electromagnetic wave with 2 parameters that were embedded within his equations, permittivity and emissivity. The speed he came up with was 299,792,458 meters per second, which was remarkably close to the figure Romer and Huygens had come up with for the speed of light. Maxwell suggested, based on this coincidence, that light was a form of electromagnetic radiation. These findings served as the foundation for special relativity, especially Maxwell's calculation of c, the speed of light. Waves typically need something to propagate in. Ocean waves propagate in water, sound waves propagate in air. In Maxwell's day, physicists thought there was a luminiferous ether that electromagnetic waves propagated in. 2 experimenters, Michelson and Morley, sought to measure the effects of the ether. The Earth spins and orbits around the Sun. That's enough motion to cause changes in the direction of the relative flow of the luminiferous ether. If the theory held, then it should be possible to observe the effects on light. Light would travel slower when the Earth's motion is going with the luminiferous ether and faster when traveling against. Their experiment involves splitting light with half-silvered mirrors and then recombining it. This device is called an interferometer. It emits a beam of light into a half-silvered mirror that splits light into two separate beams. If there are no losses, the beam intensity of each of the two beams is half the intensity of the source. The light bounces off the mirrors and then passes through the half-silvered mirrors again. And this time, half of it is picked up by a detector. If this apparatus were in motion relative to the Earth, there would be a phase shift between the beams. Imagine these are two beams of light. They're depicted here as sine waves. This isn't what light really looks like. Light propagates out in 3 dimensions. This is only a representation that depicts the wave characteristics. Here the wave crests and troughs line up. When you add these two beams together, you get twice the intensity. Shifting the phase looks like this. Here, the crests and troughs line up. When you add these two beams together, they cancel out. You get no light even though you started with two beams. This is a phase shift of 1/2 of a frequency. A phase shift between 0 and 1/2 results in some light when you combine the two beams, but it's less than the sum of each of the beams. The closer you are to in phase, the higher the intensity of the combined beam. The closer you are to out of phase, the lower the intensity. It's called an interferometer because one beam can interfere with the other and diminish the output. Michelson and Morley used an apparatus based on this principle to determine if one of the beams was slowed down relative to the other as the apparatus flowed through the ether. The apparatus is initially set up and adjusted so the two beams are in phase. That's done by moving one of the mirrors. Then, if the apparatus were oriented along the ether this way, the red beam would experience more drag than the green. If the two beams were in phase in this orientation, they would certainly not be in this orientation. Look at the small graphic on the right. Michelson and Morley didn't have to necessarily rotate their device. The Earth rotates and orbits the Sun. That motion itself would change the orientation of the device. They ran several experiments, however, and always got the same result. The light stayed in phase. The apparatus appeared to indicate that both beams traveled at the same speed, no matter what their orientation, no matter where the Earth was in its orbit or where it was along its spin axis. This became known as the most famous failed experiment in history. In Einstein's view, it proved his hunch that there was no luminiferous ether. This was the key piece of information that led to special relativity. When the luminiferous ether theory was refuted, it implied that electromagnetic radiation propagated in free space. A changing magnetic field induces a changing electric field, and likewise a changing electric field induces a changing magnetic field. They oscillate between 0 and their peak magnitude, like in the graphic, and they go out to infinity. This is what Maxwell's equations predicted. With no ether, there's no medium that the waves propagate through, implying there's nothing in space but a vacuum. We know now that there's a small bit of something in space, mostly very sparse amounts of hydrogen, but Einstein's theory holds for a complete vacuum. Einstein suggested that light would propagate in a complete vacuum. The wave on top is propagating. The one on the bottom is standing. If you're a surfer riding a wave, you'd be on a standing wave. If you're playing a guitar, the vibrations of the strings are standing waves. Einstein suggested that standing light waves were not possible. Let's say we turn on a light here. It travels at 299,792,458 meters per second. Let's now say we're observing the light in this lower frame of reference. We're located at the smiley face. Now let's turn the light on again. This time we'll travel at the speed of light. The smiley face keeps up with the beam of light. Einstein asserted this was not possible. No one had ever observed a standing light wave. That didn't prove that they weren't possible, but at the same time there was no evidence that they were. This gave Einstein a clue. If you could catch up to a light wave, then you must not be able to gain ground on it. If you couldn't catch up on a light wave, then you must not be able to gain ground on it. If you're able to go 10% the speed of light, and catch up to it by that much, then why couldn't you go faster and catch up to it more? If you can't catch up to the total speed of light, then Einstein suggested you couldn't catch up to it at all. This led Einstein to suggest that the speed of light was constant no matter how fast you're traveling. Imagine you're standing on a bridge above a lake, dropping pebbles in the water. You'd create concentric waves in the water like this. The wave fronts would propagate out at the same velocity. Now imagine a bird flies by and drops pebbles in the water at 1 second intervals. To make this work, let's say the bird figures out a way to drop the pebbles straight down so there's no forward momentum. Each of the wave fronts propagate through the water at the same velocity as the first case. The stones in this second case don't know that they were dropped by a moving bird. They fall straight down. They could have come from 8 people standing still, each dropping a pebble one after the other. The lake doesn't know where they came from. If a stone hits the water, it will create a wave that will propagate out at the same velocity as the first case, where all the stones were dropped in the same place. There's nothing in the wave motion that indicates that the pebbles were dropped by something that was moving. Rather than dropping stones, now imagine that you pulse a light on and off in the vacuum of space to create wave fronts. The light, according to Maxwell's calculations, is going to propagate out at 299,792,458 meters per second. Now, imagine you're in a spaceship moving at a constant velocity, and you pulse a light as the ship moves. The electromagnetic waves don't know that you're moving in the spaceship. Once the light pulse is emitted, a wavefront is created that propagates through empty space at 299,792,458 meters per second. It doesn't matter that they came from a moving source. In fact, this could be 8 spaceships sitting at rest, pulsing separate lights in sequence. Now turn that around. Let's say that the spaceship that pulsed the light is at rest, and we're moving at a constant velocity past it. If we were on the water, we'd be moving relative to the water. If you've ever been in the surf in the ocean, you know that when you paddle out, the waves come at you quicker. They're coming onshore and you're paddling out. You're paddling against the waves. The opposite occurs when you paddle in to catch a wave. You start paddling in until your speed matches the speed of the wave. If you're successful, you've literally caught a wave. It's a standing wave at that point. In the ocean, waves propagate through the water, and you can move relative to the water. Once Einstein found out that there was no ether, no medium in space that electromagnetic waves propagated through, he realized that there was nothing you would move relative to. If you travel past a stationary spaceship that's pulsing a light, you'd see this pattern. They would observe light propagating this way, on the left. For the case on the right, if we're moving past an emitter, then how can light still be traveling toward us at a constant 299,792,458 meters per second? An inertial frame of reference is one where you feel no acceleration. You're either traveling at a constant velocity or you're still. In both cases, you're in an inertial frame. A good test is to hold the ball in front of you and let go. If it stays where it is, you're in an inertial frame of reference. If it falls to the floor or drifts towards the wall, you're accelerating. As long as you're not accelerating, you're in an inertial frame of reference. The lower rectangle is in an inertial frame because it's moving at a fixed velocity. The upper one is also in an inertial frame too, since it is at rest. Here, the upper rectangle on top is moving at a constant velocity and the lower one is fixed. Both are still in inertial reference frames. Neither rectangle is accelerating. Here, both are moving at the same velocity relative to each other as in the first 2 cases where one was fixed. From our perspective, they're both moving. You can perceive motion in these cases because you're watching this on a screen. That's your fixed reference point. Now imagine that you're in space and it's empty, or mostly empty. There's no fixed reference. You might think that the stars provide a fixed reference, but they don't. They too are all in motion. There's nothing in the universe that's fixed. Everything moves relative to everything else. If you're in an inertial frame of reference, you feel you are at rest, and you see rectangles moving past you at a constant velocity. However, because there is no fixed reference, people in the rectangles that are moving at a fixed velocity also feel like they're at rest. Both of you could let go of a ball and it will hang in space. All we can say about these 2 rectangles in their inertial frames of reference is that they move at a constant velocity relative to each other. 2 separate observers in each frame can never agree on who is at rest and who is moving. Velocity is with respect to some arbitrary reference point. Saying that I'm traveling at a fixed velocity past a stationary spaceship is nonsensical. It's just as valid to say that the spaceship is traveling and I'm fixed. We see here pulsing lights emitted at 8 separate locations, traveling at me at the speed of light. I don't know if they're coming from 8 stationary emitters or from a moving spaceship. In fact, it doesn't matter. The light comes to me at the speed of light no matter if a single emitter is moving or if there are 8 stationary emitters. Let's say that I assert that I'm moving and the emitter is stationary. I can take that point of view. It's perfectly valid, but I didn't do anything that changes the dynamics. The dynamics are the same if I say I am moving or if I say that the emitter is moving. So if I say that I'm moving and that the emitter is stationary, the light still has to be coming at me at the speed of light. In order for the speed to change, I have to change the dynamics. Let's look at this from the point of view of a now stationary emitter. He would observe light propagating away from him at the speed of light. He can't tell if he's moving or stationary. Even in the case where I say he's moving, he still sees the universe this way. This is inconsistent with how we experience the world. This was the great genius of Einstein. He saw the world in a different way. It took a lot of imagination, and he did this when he was 26 years old. The assertion that light goes at a constant speed violates Galilean relativity. Galileo asserted that the laws of physics are the same in all inertial frames. That part is consistent with special relativity. He described a ship traveling at a constant velocity without rocking on a smooth sea. Any observer doing experiments below the deck would not be able to tell whether the ship was moving or stationary. That not only doesn't violate anything we've been saying, we need that bit of information for special relativity. Galilean transformations are mathematical formulas that transform between the coordinates of one inertial reference frame to another, where the frames of reference differ by a constant relative velocity. This is the part that doesn't work with light going at a constant speed. Galilean transformations are inconsistent with special relativity. According to Galilean relativity, if you conduct an experiment on the train moving at a constant velocity, you'll get the same results as if you were on the platform. A ball dropped will go straight down, whether you're on the platform or on the train. A ball thrown will travel over a distance, again whether you're on the platform or on the train. On the platform, the guy on the right drops his ball, the guy on the left throws his. We understand that motion since we're in the same reference frame. On the train car, the guy on the left drops his ball. From his perspective, it falls straight down, but from our perspective, it rests. It follows the same trajectory as if it were thrown. The ball that falls from his perspective picks up the velocity of the train and follows a trajectory from our perspective as if it were thrown. On the train car, the guy on the right throws his ball backwards at the same velocity that the train is moving. From his perspective, it follows a parabolic trajectory, but from our perspective, the velocity of the ball is canceled out by the velocity of the train. It appears to us as if the ball were falling straight down. To transform velocities from our fixed frame of reference to the moving frame of reference on the train, we have to add the velocity of the train. That, simply put, is a Galilean transformation. It only works this way because we have a fixed frame of reference. In space, with electromagnetic radiation, we have no fixed reference. Here's how we would apply Galilean relativity to light. This is wrong, by the way. Imagine we shine a beam of light in this direction. Now imagine that we do the same for an apparatus that moves. The light in the first case goes 299,793,458 meters per second. That equals c. The mechanics of Galileo would have us add the velocity of the apparatus v to the velocity of light to determine how fast light is going from our fixed frame of reference. That results in a higher speed. We just said, though, that light, once emitted, propagates in free space. It travels at 299,793,458 meters per second, no matter what the velocity of the source. Also, the Michelson-Morley experiment would have been successful if v was added to the speed of light. This Galilean transformation gives us the wrong answer. Galilean transformations work for passing ships, but not for light. This is fundamentally why the Michelson-Morley experiment failed. Light goes the same speed no matter what. Let's quantify this. Let's take our apparatus and flip it so that it's vertical. Here light is emitted from the bottom to the top. The length of the apparatus is 1 light second long. That's 299,792,458 meters in length, denoted by the letter C. When we turn on the light, it will take 1 second for the beam to reach the top. That's 1 second for light to travel 1 light second of distance. Let's call this a light clock. Now let's put the apparatus in motion. Turn on the light and the beam reaches the top. Now let's look at the geometry of this. Imagine a light pulse from a single emitter. The light propagates out in 3 dimensions in free space. This animation demonstrates that in 2 dimensions. The pulse starts the electromagnetic wave. From there on, it self-propagates at the speed of light, c meters per second. Let's look at the case where the emitter is moving. It doesn't make a difference. Once the pulse is emitted, the light self-propagates in free space as electromagnetic radiation. After the pulse, the emitter isn't involved anymore. The electromagnetic radiation self-propagates. Let's take some measurements of the distance light travels. Let's say this occurs in 1 second. Each of the red segments would thus be 1 light second long, the same length as our light clock. The light emanates in all directions, so all 6 of the red segments are 1 light second long. That's c meters. Now, let's superimpose our light clock on one of the beams. The light would extend out into space 3-dimensionally, but within the light clock, it goes from the bottom to the top. Our light clock is 1 light second long, so in 1 second the light reaches the top. Now, let's look at a second beam. Both the red and green travel 1 light second in 1 second. One goes straight up and the one goes diagonally. Whatever direction we choose, they're going to stay with the wavefront depicted by the green circle. Now, let's look at a moving light clock. We see the light clock moving from our perspective. In 1 second, the beam of light we observe follows the green path that is 1 light second long. But notice now, the light doesn't make it to the top of the moving light clock. It appears to only go 2/3 of the way. We observe the moving light clock registering something less than a second, in this case about 2/3 of a second. The moving clock appears to us to run slow. In 1 second on our clock, the moving clock only advances 2/3 of a second. If there were a local observer moving with the clock, we'd see him going in slow motion. This is the foundation of Einstein's theory of special relativity. This was the epiphany he had that led to his groundbreaking theory. If we observe a moving frame of reference, time will run slower in that reference frame. This is called time dilation. Let's quantify this. The red line segment is c meters long. So is the green. Let's measure the length of this line segment that's colored violet. Let's say the moving clock was moving at a velocity of v meters per second. Since c is expressed in meters per second, and since we're running this thought experiment over a second, the displacement of the moving light clock equals v meters. That's this distance here along the magenta line. Let's call this line segment A. The green line has a length c, and the magenta line has a length v. The violet line that we called A and the green and magenta lines form a right triangle. The Pythagorean theorem tells us that c squared equals a squared plus v squared. If we solve for a, we get that a is the square root of c squared minus v squared. That's less than c. For the stationary clock, the light traveled c meters at c meters per second. That equates to 1 second. The light in the moving clock, however, traveled the square root of c squared minus v squared meters at c meters per second. Dutch physicist Hendrik Lorentz simplified this. Start with the square root of c squared minus v squared. Multiply the formula inside the radical by c squared over c squared, which equals 1. Now let's put c squared under c squared minus v squared. From here we can take c squared out from under the radical as c. Now let's separate out the fraction in 2. C squared over C squared equals 1. Let's then put the square root in the denominator. In order to do that, we'll have to make it 1 over the square root. This fraction is called the Lorentz factor. It's represented by the Greek letter gamma. The square root of C squared minus V squared equals C over gamma. We can make that substitution here, and that equals 1 over gamma seconds. Time dilation of a moving reference frame is inversely proportional to gamma. The length of this segment A is C over gamma. Here's gamma plotted over a range of speeds. From the last slide, we showed that time dilation is 1 over gamma. At speeds up to half the speed of light, gamma is very close to 1. If you see someone moving past you at 100 kilometers per hour, their time will dilate, but at a very, very small factor. That's why Galilean transformations work at speeds below the speed of light. They're not exact, but at speeds below 10% the speed of light, they're only off by a very small amount. 10% of the speed of light is 29,979,348.8 meters per second. Even at only 10%, that's pretty fast. At 80% of the speed of light, gamma is 1.67. At 90%, it's 2.3. 1 over 1.67 is 0.6. If someone is going 80% of the speed of light, 1 second on our clock registers as 0.6 seconds on their clock. If someone's going 90% of the speed of light, 1 second on our clock registers as 0.43 seconds on their clock. Gamma equals 2 at 86.7% of the speed of light. If you see somebody traveling that fast, you'll observe them at half speed. Let's go back to this circle, and let's set the velocity v equal to c. This line segment will grow, and now equals c. The light clock would move out to here, and the green line segment would now be down here. Notice that there's no room for the moving light clock to register any time. Time is frozen for a light clock going at the speed of light. This led Einstein to conclude that the speed of light was a cosmic speed limit. Let's extend the moving light clock so that the beam reaches the top. This distance is now c meters. Rather than this taking 1 second, let's use the variable t for time. We determined earlier that if our time was t, the time we observe for something that's moving is t over gamma. The light clock would have to travel this much farther. The beam of light would thus travel this much farther from our perspective. We've set up two similar triangles. The length of this side c over the length of this side c over gamma equals the length of the green line, which includes the extension, over the length of the solid green line, which is also c. If we multiply each side by c, we get this. We can factor out c over c. We can then put gamma in the numerator. The distance we see the light travel is c times gamma. Likewise, the distance the light clock moves is v times gamma. The extended time is also t times gamma on our clock and t on the moving clock. This makes sense. If the time on our clock is 1 second, we'd observe t over lambda for the moving clock. If the time on the moving clock is 1 second, then the time on our clock would be gamma, 1 times gamma. There's another effect caused by relativity. Imagine a mass in motion within a frame at rest. The momentum is the mass times m times the velocity v. Now imagine the same mass is in motion at the same velocity, but this time within a moving frame of reference. Since there's a time dilation within the moving frame, it takes t times lambda for the mass to achieve the same displacement. Velocity is displacement over time. If the time shifts by gamma, then the velocity shifts by 1 over gamma. The velocity we observe within the moving frame is v over gamma. Now let's make that adjustment in the momentum equation. Notice that we divided the velocity v by gamma because of the time dilation. We also had to multiply the mass by gamma. In the first case, the mass moved within a fixed frame. In the other case, the mass moved within a moving frame. If there's no imparted acceleration, both frames are inertial frames of reference, and hence the momentums have to be the same. This is the law of conservation of momentum. Einstein suggested that in order to account for the velocity being reduced by a factor of 1 over gamma, you'd have to increase the mass by a factor of gamma so that you got the same momentum. If you observe a mass moving, the mass will increase. At speeds below the speed of light, the increase is negligible, but as you approach the speed of light, there'd be a noticeable increase. Gamma equals 2 at 86.7% of the speed of light. If you see someone traveling that fast, you'll observe them at half speed and double their mass. Think about what this does to Newton's theory of gravity. If the mass increases, the gravitational force increases proportionally. If we were to increase the mass of a moving body by a factor of gamma, the formula for the gravitational force would look like this. Gamma, you'll recall, is a function of velocity. The v squared term is the only variable in this equation. As the velocity of a planet in orbit increases, its mass increases, and hence the gravitational force increases beyond what Newton had predicted. This explains the discrepancy that Leverrier discovered Mercury's orbit. At perihelion, the planet moves faster than at aphelion. At perihelion, the mass of Mercury is greater than at aphelion. That causes a perturbation in the orbit. Here's a comparison of the orbit of Mercury from Newton and Einstein's perspective. The Newtonian animation assumes the planet follows a perfect ellipse. The Einstein animation is based on the added force at perihelion, which accounts for the precession in the direction of the orbit's rotation. This effect has now also been measured with Venus and Earth. As I said, this resolved the discrepancy that Leverrier had discovered. It actually worked the other way around. When Einstein published special and then general relativity, there was little evidence to support the theory. The precession of Mercury was cited as one of the tests that proved his theories.